Professor Gábor Székelyhidi from the University of Notre Dame. He got his PhD degree from Imperial College London in 2006. He did many important works in the related areas of complex geometry, algebraic geometry, and differential geometry. Today he will speak on extremal Kahler metrics. Please.
Well, thank you very much for the introduction, and also, of course, I'm very grateful for the organizers for giving me this opportunity to speak here. So, in my talk, I want to give a sort of kind of survey of extremal Kahler metrics, like different ideas that are involved, and the field is very much open, so I won't be able to give an impressive list of theorems like in the previous talk, but hopefully it will give you the idea that this is an exciting field to work in still. So first of all, let me explain what are extremal metrics. Well, the motivation is a sort of very fundamental question in differential geometry. Namely, if you're given a manifold, is there some sort of best shape? Like, can you give some kind of optimal metric on it? And perhaps the most well-known example of this is the uniformization theorem. So roughly speaking, this says that on a closed surface, in every conformal class of metrics, you can find an essentially unique metric with constant curvature. So it's unique up to isometry and scaling. So this is a really fantastic theorem, and a natural question is whether there are higher dimensional generalizations of this. So of course there are many different directions that you could go into. A very well-known one is the Yamabe problem in conformal geometry. So there you simply replace surface with higher dimensional manifold and constant curvature with constant scalar curvature. And it's well known that the theorem is still true due to work of many people like Aubin and Trudinger and Shane. Of course, the uniqueness in some cases will no longer hold. Well, the scalar curvature is quite a weak property of a metric. So if you want something much stronger, then you'll get a much weaker result. So already you have to really restrict the dimension, and Thurston's geometrization problem was, perhaps the motivation was to find, say, a constant curvature metric on every through manifold. Of course, this is way too ambitious. So what it turns out that instead what you can do is break up the manifold into pieces, each of which admit one of 8 sort of nice geometries. So the problem that I will talk about has some common features with both of these sort of higher dimensional ideas. Well, the field that it's in is Kähler geometry, so I have to quickly tell you what that is, in case you don't know. So a Kähler metric is a metric on a complex manifold that interacts in a very nice way with the complex structure. So first of all, it's Hermitian. So here the I is just multiplication by I in the tangent space. So on a complex manifold, each tangent space is a complex vector space. Okay, so G is a Hermitian metric, and it has this other very nice property, namely that if you construct this 2 form out of the metric and the complex structure, with this omega, where you combine G and this multiplication by I, so this is easy to check that it's anti-symmetric, so you get a 2 form. But the crucial property is that it's closed. That's what it means to be a Kähler metric, and this omega is called the Kähler form. The reason why it's very nice that it's closed is that then it defines the rank cohomology class, which is called the Kähler class of the metric. And this is a sort of fundamental topological invariant of the metric. Okay, so this Kähler class is going to be what plays the analog of the conformal class in conformal geometry. So the problem that led to the discovery of extremal metrics is to find a best or canonical representative in a given Kähler class. So Calabi, when he was faced with this problem, he decided that the best way to do it is to try to set up some variational problem, which in fact is very similar to, it's a sort of intrinsic analog of the Willmore conjecture, where here you want to minimize the L2 norm of the scalar curvature rather than the L2 norm of the mean curvature. Okay, so an extremal metric is the definition is that it's a critical point of the functional, which to every metric in a given Kähler class associates the L2 norm of its scalar curvature. So then, of course, you can compute what the Euler-Lagrange equation of this variational problem is, and you find that a metric is extremal if the gradient of the scalar curvature is a holomorphic vector field. So this is some vector field, and it needs to preserve the complex structure. So this is perhaps the first indication that this is kind of a natural problem to look at. It has some nice interaction with complex geometry. In addition, it turns out that the scalar curvature could be replaced by the Ricci curvature or the full curvature tensor, and you get exactly the same critical points. So it's really a sort of natural thing to look at. Okay, so to be a best or canonical metric, you better be unique. And in fact, this has been proved. This is a highly non-trivial theorem in sort of different cases of generality that follows from work of Calabi, Van Dunamucci, Donaldson, Chen-Tian, and Bernson. So the main remaining question is whether such a metric exists in every Kähler class. So I think I can give a spoiler that they do not always exist. So that will be a key point of this talk. Well, first let me give you some examples. So you remember extremal meant that the gradient of the scalar curvature is holomorphic. Well, in particular, if the gradient is 0, then it's a holomorphic vector field. So metrics with constant scalar curvature are always extremal. And I'll abbreviate this as CSCK for constant scalar curvature Kähler. So for instance, the metrics given by the uniformization theorem are extremal. Then the next vast class of examples is provided by the celebrated work of Yao and also Aubin on Kähler-Einstein metrics with non-positive Ricci curvature. So then the work of Tian in 1990 classified all Kähler-Einstein metrics with positive Ricci curvature on surfaces. So that again gave lots of examples. So these Kähler-Einstein metrics have constant Ricci curvature. So in particular, it's constant scalar curvature. And okay, there are many other sporadic examples, but one sort of large theory is the theory on toric surfaces developed by Donaldson and Li Sheng. So this also provides many examples. Let me focus on one particular example, which will show up several times in this talk. So if you take, say, a genus 2 Riemann surface, and then what you want to take is a manifold which is a sphere bundle over this. So if you want to be precise, it's this projectivization of a certain rank 2 bundle on the surface. But if you just imagine a bundle of spheres parametrized by the surface. So it has complex dimension 2. So, well, this problem really depends on what Kähler class you choose. And for this particular complex manifold, the Kähler classes are essentially parametrized by just one number. So this number is how big these fiber spheres are compared to the base. And then up to scaling, that there is one further invariant, just scaling everything up or down. So if you fix the area of the 0 section, then you just have to pick how large the fibers are. So it turns out that when the fibers are very small, in fact, it doesn't have to be extremely small, up to some well-defined value, then you can find an extremal metric. So this was the work of Tones and Friedman. The result follows from sort of ODE analysis. So in fact, you have an extremely concrete description of these metrics, and then you can study what happens as the size of the fibers approaches this critical value. And what you find is that when they're very small, then the fibers are isometric to just round spheres. But as you grow, it sort of starts having this kind of neck pinching behavior. And then as you tend to the limiting value, then actually the diameter goes to infinity, and the manifold breaks into 2 pieces with complete extremal metrics. So this you should imagine that so this is a bundle of spheres. So each sphere, they're all isometric to each other. Like all the action just happens on the fiber metrics. Well, and it turns out that like this picture suggests, there is actually no extremal metric on this manifold when the fibers become bigger than this special number. So this was the work of Apostle of Kähler, Goduchon, and Tones and Friedman. Okay, so this is what I was suggesting, that these extremal metrics don't always exist. And so really, of course, the fundamental question is, can we decide in which situation they exist or not? And the central conjecture in the field is that the existence of extremal metrics is related to some sort of algebraic geometric stability condition, at least when the Kähler class is actually algebraic. So if you know algebraic geometry, so this is the case when your manifold is actually a projective variety, and by the Kodaira embedding theorem, that's equivalent to saying that the Kähler class is actually an integral cohomology class. So anyway, this is the case in which algebraic geometry can say something, and the conjecture is that M admits an extremal metric in one of these integral Kähler classes, if and only if M, so when you have an integral cast, it's always associated to a line bundle. So you want this M paired with this line bundle to be what's called relatively k-stable. Okay, so I will explain what that means in the next couple of slides. So to explain, I have to go to a completely algebraic direction for a couple of slides. So if you have a projective variety, then you can say, you can define something called a test configuration, which is simply choosing an embedding and then choosing a C-star action on the ambient projective space. Well, so now you can imagine your manifold sitting in projective space, and you have this C-star family of automorphisms sort of pushing it around. And what you can do is see what happens when you let the parameter in C-star go to 0, to the origin. And in algebraic geometry, you can define a sort of limit, which could be some highly singular object, but it's best to think of it as just some purely algebraic construction. But in any case, given this limiting object M0, you can cook up some number called the generalized Futaki invariant. So I think it would be completely unhelpful if I told you what the definition is, but it's something you can really just compute. You can plug it into a computer or do it by hand. So let me give a very simple example. So suppose M is just the projective line. You embed it into the projective plane as a conic, and we consider this C-star action on the CP2, which acts just by diagonal action with weights 1, 0, 0. So it only acts on the first coordinate. So it's very easy to compute that the image of M will be this slightly different conic, xz minus ty squared. And then as you let t go to 0, your nice conic degenerates into the singular one, which is just the union of two lines, xz equals 0. Okay, and then if I told you the definition of the Futaki invariant, I'm sure you could compute that you get a half. And it's important that this is positive. So the sign matters because that's what the definition of k-stability involves. Okay, so if we have one of these projective varieties, so remember this is encoded in a manifold together with the line bundle, which the line bundle is basically telling you what the Kähler class is. So this is k-stable if for all possible projective embeddings using pairs of this line bundle and all possible ways of degenerating the manifold using C-star actions, this number is positive. Except for very trivial ones, like one that doesn't move the manifold at all, or that you can get 0. Again, in the conjecture before, I had this phrase relative k-stability, so this is simply a sort of extension of the notion of k-stability to deal with extremal metrics, because the original notion was designed to deal with constant scalar curvature ones. Okay, and then just as an example, so CP1 and O1, so this means that you just consider it as a projective subvariety of itself, so it's just a line. This is k-stable. For instance, the Futaki invariant that I showed you in the previous slide was positive. But that roof surface example that I had a couple of slides ago is not relatively k-stable when the fiber size becomes very big. And in fact, you can show that with a very similar degeneration as what I showed in the CP1 case. So it turns out that you can degenerate this ruled surface in such a way that all the fibers break up into just 2 lines. And if you do the relevant computation, you'll get a negative number once the fiber is very big. Okay, so going back to this conjecture, so now you understand relative k-stability. So once again, the conjecture said that M admits an extremal metric if and only if it is relatively k-stable. So one direction of this is basically completely understood, and it's again due to the work of many people, like Tian, Donaldson, Mabuchi, Stoppa, myself, and Berman. And probably the most exciting development in this field is the recent solution of the Kähler-Einstein case of the converse direction. So this says that basically this tells you when a manifold admits a metric with Kähler-Einstein metric with positive Ricci curvature. So this is due to Chen, Donaldson, and Sun from 2012. Unfortunately, so the more general case is pretty much open, and in fact, it is probably false. So there's not much use working on it as it's stated. So this is due to an example of a hostile of Kahler, Gábor, and Friedman. So actually it's quite a simple example. It's very similar to this ruled surface that I gave you, except it's a sphere bundle over a higher dimensional base. And what one finds is that one can show with some method that it does not admit an extremal metric, but all indications show that it is relatively k-stable. Okay, we cannot prove that it is relatively k-stable because it's almost impossible to prove that anything satisfies the stability condition, but I don't think anyone believes that it is not stable, so it's almost certainly a counterexample to this conjecture as stated. So what this means is that even before discussing progress on this, we should really formulate some more precise version, which has some hope to be true. Okay, so we need some stronger notion of stability than relative stability. So let me just very quickly describe one approach to this and try to explain what it achieves. So the first observation was due to Witt-Nystrom, that if you have a test configuration, so remember this was just a C star acting on some embedding of the manifold, well, this can be encoded in a filtration of the homogeneous coordinate ring. So a filtration is just this standard algebraic notion. Essentially what you do is you take the weight filtration of the C star action. But then it's a very simple idea to say, well, why can I not take, that the filtrations you get this way are just special in the sense that they're finitely generated. So this means if you know the filtered pieces up to some finite number of terms, from that you can deduce everything else. So it has some finiteness property. But then you can ask, well, why don't I just allow more general filtrations? So you can do this, and if you're able to define some sort of Futaki invariant for arbitrary filtrations, then you can formulate a stronger notion of stability. So you can require that this more general Futaki invariant is positive. Okay, so this is the first theorem that I state. So we were able to show that if M admits a constant scalar curvature metric in the scalar class given by a line bundle, then this generalized Futaki invariant is positive for all non-trivial filtrations of the coordinate ring. And in particular, this resolves this counterexample. So maybe to give a sort of very simple idea, just some intuition of why this might help. For this particular example, so as I said, it's this ruled manifold over some high dimensional base. One can show that for every rational number from between, say, 0 and 1, you can obtain a test configuration. There's some way to associate one. But you get a filtration to every number between 0 and 1. So basically what's happening is that you have some function which is positive at every rational value. So you do not see any instability. The test configurations do not detect anything, but there's some irrational value where this attack invariant is 0. And then you need these non-finite generated filtrations to detect that. Okay, so just to state it, I believe that this would be a sort of improved version of the CIT and Donaldson conjecture, that M admits a CSCK metric if every filtration has positive attack invariant. Okay, so let me talk about some existence results. So as I said, beyond the Kähler-Einstein case, it's very unlikely that, it's a much more difficult problem to prove some general result. So then what you remain with doing is to do some simple special case. And one class of examples that can be studied really effectively is like perturbation results. So the result I want to talk about is on blowups. So very quickly, if you have an extremal metric on M, so you pick some manifold that you already know admits an extremal metric, and then you pick a point. Then you can consider what is the blowup of the manifold at this point. So this BLPM, and this blowup admits a natural family of Kähler classes. Very simply pull back the base class and subtract a small multiple of the exceptional divisor. So if you're not familiar with algebraic geometry, just imagine that what you're doing is that this point P, you're doing some sort of surgery which replaces the point with a copy of projective space. And this parameter epsilon is telling you how big this projective space is. So when epsilon is very small, then you're doing some very small surgery where you glue in some sort of very small projective space at this point. Okay, and then a question is whether this blowup admits an extremal metric. So the first very general theorem in this direction was due to Arezzo and Packard in 2006. They showed that if the manifold has a trivial automorphism group, then the blowup admits a CSCK metric in these classes when the thing you glue in is sufficiently small. So I guess if the automorphism group is trivial, then the original extremal metric is also constant scalar curvature, because this holomorphic vector field given by the scalar curvature has to be trivial. So actually, Packard, in his ICM address in 2010, basically asked what one can do if this automorphism group is non-trivial. And in fact, he obtained many results with Arezzo and Packard, and then together with Singer, but they were all assumed with a lot of conditions that were hard to check. My theorem is to basically completely solve this in the case when the dimension is bigger than 2, so we get a precise characterization of when the blowup admits a CSCK metric. So maybe I should just say one thing. So in this result about Kähler-Einstein metrics, so I said that it's already known that the K stability implies the existence of a Kähler-Einstein metric. The problem is that, as I said, it's impossible to check whether something is K-stable. So in particular, that theorem has not given rise to a single new example, even though it's of course of tremendous theoretical importance. The reason why K-stability is so hard to check is because you need to check all of these projective embeddings. So you're embedding into projective spaces of arbitrarily large size, and then considering all possible C-star actions. So it's a sort of infinite dimensional algebraic problem. Well, in this case, it's actually a very simple notion of K-stability that you need. The only sort of degenerations that you have to consider come from the automorphism group of the manifold. So, that's sort of expected in these general perturbation problems. So this is actually in any example, you could check whether the blowup admits the CSCK metric or not. So let me just give a brief sketch of the proof for anyone who has not seen these kind of arguments in geometric analysis. So the idea is, like I said, the blowup is some kind of surgery So what you want to do is sort of glue in some sort of model metric. So more precisely, you start with this extremal metric on your manifold M, and then near the point P, the metric, if you sort of zoom into a very small scale, the metric will be roughly flat. So then you could try to glue in something else, which is sort of approximates a flat metric near infinity. So in particular, there is the so-called Burns-Simanka metric on the blow-up of Cn at the origin, which is asymptotically flat. And then when you scale that down by some very small factor, then the sort of edges of that roughly match up with this, the flat metric near the point P. So you can just kind of glue it in with some cutoff functions. What you get from this is you'll get a metric which is still extremal, sort of away from the point, like you haven't changed it at all, and it will have constant scalar curvature in the little piece that you glued in. So in particular, in some suitable function spaces, you can show that this is very close to being an extremal metric globally on this blown up manifold. So then you try to perturb this. Well, you want to use some sort of inverse function theorem with estimates, so you need to control the inverse of the corresponding linearized operator. But in general, the problem is that this is obstructed, because when the automorphism group is non-trivial, then that precisely gives you the co-kernel for the linearization. So it's precisely the obstruction to just perturbing the metric. So then, okay, I mean, you have to do a bunch of calculations, but of course the key idea is to somehow relate this obstruction to k-stability. And I guess the sort of simple observation is that the obstruction is also helping you at the same time, because if you have a point, so P, where you're trying to blow up, well, if your automorphism group is very large, then this point P will have a very large group, a very large orbit under the automorphism group. And if you blow up at any other point of this orbit, you end up with the same blow up. So instead of just being able to blow up at P, I can move to different points and try blowing up there. So you get this sort of huge degree of freedom, I mean, precisely compensating for the big co-kernel. And, well, I mean, there are lots of technical details, but this is what sort of helps you still get the existence result. Okay, so there are many kind of further questions along these lines that one could do. So it's, some of this is also work in progress. Well, the first question is also, of course, to try to remove this dimensional hypothesis. So if you remember, I had to assume that that dimension is bigger than 2. Okay, so that's a sort of technical thing, and probably the same methods will work for that. Also, of course, you would want the same thing for extremal metrics, not just CSCK, and again, that's probably a more subtle technical thing, but it will probably be possible. But then a question you could ask is, well, can we blow up some higher dimensional thing instead of just points? So there you're gluing in something higher dimensional, and in particular this problem becomes sort of non-local. It's no longer just a sort of local problem near the point, but you have something which is global. So here several issues arise. The main thing is that there is no analog of this sort of model metric. Like you don't know what to glue in. Another interesting question is, well, so here I only blew up one point, and there you see that, well, there is a strong condition for the blow up to admit the metric, namely you need the stability. But there is reason to believe that if you're allowed to blow up lots and lots of points, like all over the manifold, then maybe there is no condition on the original manifold, and you can always achieve a constant scalar curvature metric. So this would be analogous to a famous result of Taub's on anti-self dual metrics. I mean, basically the idea is that every time you do this gluing, then that little region that you get is sort of very nice. In this case, it will be scalar flat. So you could imagine doing this everywhere on the manifold, and then you made most of the manifold scalar flat. So of course it's not quite true, and there are lots of difficulties, but I think there is reason to believe that this is true. And in fact, there is a simple example one can construct of a manifold that does not admit a CSCK metric, but if you blow up at almost any point just once, then it will admit a CSCK metric. Okay, so finally, let me talk a little bit about what we can say when no extremal metric exists. So remember, extremal metrics were critical points of this L2 norm of the scalar curvature, and in fact, one can show that they always minimize this functional. So this in particular follows from this theorem of Donaldson. So this theorem, well, let me just, so of course, if there is no extremal metric, you can still ask what happens if you try to minimize this L2 norm. So what does the minimizing sequence behave like? And so this theorem gives some sort of hint that this is related to some algebraic property. So it says that if you have any ample line bundle, so in other words, an integral Kähler class, then the infimum of this L2 norm of the scalar curvature is always at least the supremum of like minus the Futakian variance of all possible test configurations. So in particular from this you can see that if M admits a CSCK metric, well then the left-hand side is 0. So this S hat is just the average, which is a topological invariant. Okay, so if you can achieve S hat, then the left-hand side is 0. So in particular, all the Futakian variants have to be at least non-negative. So this already almost gives you one direction of this Yarati and Donaldson conjecture. But the conjecture that Donaldson made was that, in fact, you have equality in this theorem. So that's telling you something like much stronger. It's sort of telling you the existence of metrics with certain energies of the scalar, of the certain L2 norms of the scalar curvature. So I guess one thing that I haven't mentioned, but experts would know it, is that, of course, all of this theory is completely analogous to the theory of vector bundles. So the work of Atiyah and Bott, for instance, on Riemann surfaces. So everything is done by analogy to vector bundles, and for instance, this conjecture is known for vector bundles. It's due to Atiyah and Bott. Okay, so let me give you one example of this theorem when we know that it holds. In fact, as far as I know, this is the only non-trivial example where we have equality. So going back to this genus 2 curve and the sphere bundle over it, so this complex surface that I talked about before, what I can show is that, in fact, you have equality for every choice of line bundle. So the proof of this is essentially completely explicit. What you do is you simply compute both halves and you show that they're the same. So what you need to do is you have to write down certain metrics and compute what how the scalar curvature behaves, and parallelly to that, you have to write down certain test configurations and understand what that behaves, what the Futakian variants are. So it turns out that somehow the only way to do this is to do the two things at the same time. But anyway, you can do it, and I think what's interesting is what you get in the end. So it turns out, so remember, when the fibers were very small, then there was always an extremal metric, and as they increased, then you had some sort of degenerating happening. So it turns out that if you take fibers much larger even than that, then you have some very interesting behavior for these minimizing sequences. So what happens is that you sort of break up into what I would call 3 different pieces. So the 2 end pieces, again, these are just the fiber metrics. So you should imagine this like a bundle of these over a 2-dimensional surface. So you'll have 2 pieces which admit complete extremal metrics, and again, they have infinite diameter, which I cannot draw. And the middle part is, is just a vibration of cylinders. There, the circle part collapses, but at the same time, the whole thing has infinite diameter again. So you should imagine a cylinder where you fix the area, but then you make the width 0, so it goes out to infinity. So I think the reason why this is interesting is because it's very hard to model this algebraic geometrically. So it's, in the limit you get some sort of odd dimensional thing, and it's not clear what this means in algebraic geometry. But this equality tells you what it should be, because you should just look at what the corresponding maximizing sequence is on the right. Okay, and again, this you can do very explicitly. So it turns out that what you have to do is similar to this very simple example that I gave you, where a conic broke up into just the union of two lines. But instead you have to consider a very high degree line inside some huge projective space, and then you can make that degenerate into a very long chain of lines, each normal crossing the previous one. So what you'll see is sort of the first piece will have some nice large degree, but then you have lots of degree 1 lines, like a chain of them, and then at the very end you'll have another piece with large degree. So the sequence, so in the sequence what you have to do is just do this, but in larger and larger projective spaces, so that you're allowed to take longer and longer chains in the middle. So of course it should be clear that from this you don't expect to actually have a test configuration which achieves the supremum on the right-hand side, because the sequence needs larger and larger projective spaces. But it turns out that this limit can actually be encoded as a filtration of the coordinate ring. It simply won't be finitely generated. And well, I can again say like roughly what, like just to illustrate what the difference is between filtrations and test configurations. So in this case, you can show that every piecewise linear convex function gives rise to a test configuration of this M. So for test configurations, you need some piecewise linear, in fact, rational piecewise linear convex function. Whereas for filtrations, you can allow an arbitrary convex function on the interval, let's say 0 to 1. So the limiting filtration corresponds to a convex function, which is sort of linear for a while. Then it has this nice convex piece, which is not at all piecewise linear, some nice smooth piece. And then the end is again a linear piece corresponding to this large degree P1 at the end of the chain. And this filtration should be thought of as analogous to an analogy with vector bundles. This is analogous to this harder Narasiemann filtration. Okay, well, at the very beginning of the talk, I told you these two different ways of generalizing the uniformization theorem, so the Yamabe problem and this Thurston's geometrization. So I also said that these extremal metrics share features with both, and I guess I just want to point out what the features are. So I think the analogy with the Yamabe problem is very clear. You're looking at a certain class of metrics, and essentially you want to minimize some energy involving the scalar curvature. But what I want to argue is that this sort of collapsing behavior is what should be thought of as analogous to breaking up the manifold into pieces, each of which admits some sort of geometry. So the nicest geometries are where you obtain extremal metrics, like these two end pieces. But then there are some other geometries where you have various collapsing behaviors. And I think what would be great is to have almost any other example of this. So yes, my question is, can one generalize this picture that happens for rude surfaces? Okay, and with this, I'll end my talk. Thank you for listening.
Thank you very much. Are there any questions, comments? Yeah, please.
Yeah, I want to ask about this generalized filtration, which is not finely generated. Is there a way to interpret this geometrically, maybe in analytic geometry, rather than algebraic geometry, to give a nice interpretation?
I mean, I'm not sure. It would be very nice if there were more interpretations, but I guess I think to me one of the sort of main issues is how would you go, what is some sort of analytic way to see this? In particular, if I have, say, an arbitrary family of Kähler metrics in a Kähler class, and they degenerate, even assuming in some very nice way, like how do you extract a filtration from that? So yeah, what is the sort of analytic correspondence, the corresponding analytic behavior? But I don't know. The only way that I can formulate it is just purely algebraically.
I'm thinking of something like power series instead of polynomial.
Oh, I see what you mean. Yeah, I think maybe that's possible to use power series. You mean, for example, take the total space of the line model, and then instead of all these degrees, you have a filtration on the ring of analytic functions or something like that. Yeah, I think maybe that's possible, but I have not really explored that.
Any comments? I have one question. Do you know any concrete example that the naive Aug19 conjecture doesn't hold for general polarization?
Was here this example of apostolov?
Apostolov.
I mean, so it applies to extremal metrics, and as I said, so it's not. I think almost everyone expects that this is an example that is relatively k-stable, but it's known that it does not admit the extremal metric, so it's almost certainly a counterexample.
I see. Yeah, thank you. Let me. This is a gift from the local organizers.